So in this lecture, we're going to cover what's known as a voltaic cell, which is also called a galvanic cell, which is also a battery, which is also called an electrochemical cell. So all the same thing. So basically, if we set up a couple solutions, so if we put a strip of metal in here, so maybe this is zinc metal, and put a strip of metal in here, so maybe this is copper, and if we're in an aqueous solution, then we can connect the two with a wire, and then maybe in the middle of this wire is a voltmeter, or it could be a light bulb or an appliance, something like that. And then in solution, so we have something like zinc cations, and so maybe zinc sulfate. So basically we want an inert anion that's not going to do anything. It's just going to be present to maintain charge neutrality. And in the other solution, we'd make a solution of like copper sulfate. Okay, so then what can happen in this reaction is that a zinc atom can lose 2 electrons and go into solution as zinc plus. So it loses 2 electrons, and then where do those electrons go? They could go through the wire, through a voltmeter, or through a light bulb or an appliance, so you could have current, so you could use this for electricity, and then those electrons would end up on the surface of the copper. And then what could happen is the copper 2 could pick up those 2 electrons, so you get copper 0 plating out onto the surface of the copper strip. Okay, so this needs one more piece of the puzzle to finish the voltaic cell to make this work. And the issue is that you must maintain charge neutrality in the solution. Right, if you have positives, you have to have the same number of negatives to balance them out. If you have negatives, you got to have the same number of positives to balance them out. And so every single time one zinc atom loses 2 electrons and goes into solution as zinc 2 plus, you no longer have charge neutrality, because now you have more positives than negatives. And every time a copper picks up 2 electrons to become copper 0, now you have more sulfate, SO4 2 minus. So now you have, and this should be SO4 2 minus. Now you have more negatives than you have positives. So that can't happen. So in order for this to function as a battery, you need one more piece of the puzzle. Right, you need what's known as a salt bridge. So typically could be something like potassium chloride. And then at the end of this tube, you have a semi-permeable membrane. So what that means, only select things can pass through it. Right, so in this case, zinc and 2 and copper 2 and sulfate can't enter the semi-permeable membrane, so you don't have any chance of the 2 solutions mixing together. So what's going to happen now is every time a zinc 2 goes into solution, then 2 Cl minuses is going to go into solution from the salt bridge to maintain charge neutrality in the left cell. And every time a copper 2 comes out of solution, now you have more negatives than positives, so potassium's got to go the other way, and 2 potassium's got to come in for every 1 copper 2 that comes out. And now you've maintained charge neutrality. And so now you have a functioning battery at this point. Zinc can lose electrons. Those electrons go over to the copper metal. Copper 2 picks those electrons up. And so electrons can flow through the wire, and then what flows through the solution is the ions. Potassium and chloride flow through the solutions, and that completes the circuit, and now you have a battery. Okay, so this is a half cell, and this is a half cell. So we could write what's known as the oxidation and the reduction reaction. So basically what's going on in this half cell on the left is zinc is going to zinc 2+. How does it go from no charge to +2 charge? By giving away 2 electrons. So you can think of 2 electrons as a product of the reaction. And in the half cell on the right, so copper 2 is going to copper 0, so making more solid copper. So it's going from aqueous solution to solid. So how does it go from +2 charge to no charge? By gaining 2 electrons. So that would be what's known as the 2 half reactions. Sorry, when I say half cell. Okay, so some terminology you should know. So oxidation and reduction. So oxidation is the gain. Oxidation is gain, right? Oil. Reduction. No, reduction is gain. Oil. Oxidation is loss. Oh, I always have to remember the acronym so that I remember it myself. So oxidation is loss of electrons, and reduction is gain of electrons, right? So oil. RIG is the acronym, one way to help memorize this and remember this. So the half reaction on the left with the zinc, so zinc is losing electrons, so oxidation is lost, so this would be the oxidation reaction. And copper 2+ is gaining electrons, so that would be the reduction reaction. So other terminology you should know. So what is the oxidizing agent, and what is the reducing agent? So the reducing agent is the one so it is a specific compound that loses electrons. So it's not the entire process, it is the exact thing that lost electrons. So what lost electrons in this reaction in the above is zinc, zinc solid. So it is known as the reducing agent. It is the exact compound thing that lost electrons. And the oxidizing agent is the species that gains electrons. So it's not copper, right? It's copper 2+. That is what gain the electrons. So then it would be the oxidizing agent. So it gained electrons. So it caused the oxidation of zinc. And zinc lost electrons, so it caused the reduction of copper 2. Okay, so how do you know in a cell like this which way is it going to run? How do you know that zinc is going to lose electrons to copper 2? How do you know it's not going to go the opposite direction? How do you know that copper is not going to lose electrons to zinc 2? And zinc would come out of solution. So basically, so which way the cell will run forward or reverse depends on so it depends on which species wants to gain or lose electrons the most? You know, so does zinc want to lose electrons more than copper, or does copper want to lose electrons more than zinc? Does zinc 2 want to gain electrons more than copper 2, or does copper 2 want to gain electrons more than zinc does? And so that tells you which way the cell is going to work, forward or backwards. And we'll talk about that in the next lecture, how you figure that out. Okay, so other terms for you to know: the anode and the cathode. So the anode is where electrons are lost, and the cathode is where electrons are gained. So if we go back to this cell, so then this is the anode, because that's where electrons are being lost from, and this would be the cathode, because that's where electrons are being gained at. So the copper 2 is gaining the electrons to become copper 0. So the cathode is where reduction occurs at. And anode is where oxidation occurs at. Okay, so there's a shorthand notation for how to depict for an electrochemical cell. So the shorthand notation for this electrochemical cell that we just constructed would look like that. So you always put the anode reaction on the left and the cathode reaction on the right. And so the symbol here, the line, is a phase barrier. So zinc solid, this is a solid, and zinc 2+ is in solution, aqueous, so there's a phase transition there. And same is true here. That just means there's a phase transition from solution to solid. And the double lines in the middle means a salt bridge. Okay, so one thing you should be able to do is, if you're given a depiction like this, to take that and write the shorthand notation for the cell, or opposite, if I give you the shorthand notation for the cell, be able to sketch out what an electrochemical cell looks like. And so you can also write this as the chemical molecular equation. So if we wrote this as the molecular equation, zinc plus copper 2 would make zinc 2+ plus copper 0. So basically that's what's happening in the reaction. It's just happening in two separate electrochemical cells. So you could do this reaction just in a beaker. So if you just put the zinc in a solution with the copper 2, then basically what would happen is zinc would give up 2 electrons to copper, and so then zinc would go into solution as zinc 2, and copper 2 would pick up electrons and come out of solution. So we would deposit onto the surface of the zinc metal. So that's that would be the chemical reaction going on, but this is not very useful because can't harness the electron transfer. So in all oxidation reduction reactions, that's what they are, is they're electron transfers from one thing to another thing. So you could not harness the electron transfer in the form of electricity if you put everything in the same cell, in the same beaker together. And so that's why for these type of reactions, you put them in two separate beakers and you connect them by a salt bridge that has semi-permeable membrane so that the zinc metal can never come in contact with the copper too. Because if they ever come in contact with each other, then the electron's not going to go through the wire. The electron's going to go directly from the zinc metal to the copper 2 in solution. So then another thing that you should be able to do is, if you're given this cell notation, be able to write it in chemical equation form also, or vice versa. If you're given it in the chemical equation form, be able to write it as a cell in the cell notation and be able to sketch what that voltaic cell would look like. Okay, so hopefully you understand what voltaic cells are and the different terminology associated with it.